Okay, so in this presentation, I'm going to go over an introduction to energy. For this presentation, I'm going to go over this first large bullet point. Basically, what is energy, different forms, different units, the sort of beginnings of unit conversions, but we're not going to get into factor labeling until later. Um, but really, like, what is energy? What does it really mean to have and use energy? And so make sure that before you listen to this PowerPoint or watch this PowerPoint, that you watch the video that's posted on the course website, and there's also a short reading that's posted on the course website. So please watch that here. It's also linked if you would click on this part of the presentation on your PDF file. It'll take you out to the video too. Okay, so what is energy? I want you to press pause for a second and think about what they said in the video and how they define energy. So basically, energy is, from a thermodynamics perspective, from sort of like the physics perspective, is the ability to do work. Um, Another way to think of it, it almost seems like an oversimplification. It does things for us, or it makes things happen. Um, it sounds almost like glib and, um, an oversimplification, but really it's a pretty accurate statement. I mean, energy does things. I mean, anything that you see, I mean, take a look around you in the room right now. Anything that's sort of doing something, making a sound, make the screen that you're looking at right now, anything that's emitting some light, it's using energy. So energy makes those things possible. Even if you look out the window and you see the sun, that the sun you see because of energy. The fact that you can see it is due to energy inside of your body. So energy makes things happen. It makes almost everything around you happen. It really, without energy, nothing would be truly happening. Even to think requires energy. Your brain requires electrical energy to operate and chemical energy. And so we think about, I want you to sort of take a minute to think about some things that have or use energy. And actually, literally, it's everything. If you take that word literally, everything. So everything around you has energy in it. And most of the things around you use energy or have used energy at some point in their life cycle. So just a couple of examples, you could look at battery has electrical energy, it has chemical energy stored inside that's converted to electrical energy. The human body uses energy. The sun is just a giant nuclear fusion reactor in the sky that's just spitting out energy constantly. You look at a college campus or a building, they're using energy. You're using lighting energy and heating energy, cooling energy, and so forth. I mean, the Earth uses energy. The Earth has energy, but it's also using energy constantly, every millisecond of every day. Light bulbs use energy. Heating equipment uses energy, right? So energy is everywhere. It's all around you. It's literally all around you. It's surrounding you right now as you're sitting here listening to this. So everything has energy. Basically, everything around you has used energy, or not basically, everything around you has used energy at some point in its life cycle. So let's think of just a couple. Let's try to sort of wrap our minds around what energy really means. So it's in everything around you. But what does it really mean? What is energy? Okay, so remember, it's the ability to do work. Now, the ability to do work just means work. It means the movement of energy from place to place. So, you think of it as energy is required to do things, to make things happen. Okay, as I indicated earlier. So let's look at a couple of examples. So here are some things that contain energy. Gasoline, obviously, wood, the nucleus of every atom around you. The fire has energy, a person has energy. I mean, you can look at everything on here. This concrete has energy, this grass has energy, there's energy in the metal here. I mean, there's energy everywhere. So let's start to try to sort of think, okay, well, all of these things have energy. What does it really mean to have energy? And what does it mean to what is energy like? What is energy? Okay, what is it made of? So I really hope that you can start thinking of energy in these terms. I want you to think of it as an amount of something. So energy is in everything around you, is being used by everything around you, or at least has been used by everything around you. But you can actually quantify that energy, whether the energy, if you see an object sitting next to you, you can quantify the amount of energy that's in that object. Okay, so energy is an amount of something. It's a discrete amount. You can measure it, and you can it's a unit of something. So let's just look at a quick example. So I give you a gallon of gas. All right, is there a lot of energy in there? Yeah, you can do a lot with energy. What can you do with it? You could burn it, you could use it heat, you could run a car on it, and so forth. What if I give you 100 gallons of gas? Okay, so you take your 1 gallon of gas and you compare it to your 100 gallons of gas. It's probably very intuitive that the 100 gallons of gas has a lot more energy. So there's energy in gas. So if you have more gas, you have more energy. Okay, so energy is an amount of something. Gasoline has an amount of energy. More gas means more energy. Okay, so what if I give you one toothpick? Does a toothpick have energy? Can you do something with the toothpick? Okay, of course. I mean, you could burn a toothpick. You could technically convert it into energy in a couple different ways. Burning is the easiest way to think of it, but it has energy. I mean, P. Diddy has energy, in this little toothpick in his mouth. Does it have a lot of energy? Well, not really. Think about all the heat that would be given off if you burned that toothpick. Now compare that to, a couple of cores of wood, a big giant wood pile, right? So this is wood, this toothpick's wood, this is wood. So which of these has more energy? Obviously, the wood pile has a lot more energy. Um, So I want you to think energy, this toothpick contains energy. It has an amount of something, amount of something. Well, this woodpile has the same something, but has a lot more of it. And that something it's matter, but it's also energy, okay? So think of it as an amount of something. Again, wood contains energy. If you have more wood, you have more energy. All right, one last little example. Say you have the heat from one match, okay? That's energy. It's spitting out this radiant heat and a couple other forms of heat, electromagnetic from the light and so forth. So, okay, so there's some energy in the match you can think, as warm, it sort of represents energy. That's the sort of realization of energy. So it has some energy. We'll compare that to the amount of energy from a giant, fire, whether it's a house fire or a giant bonfire, whatever, right? So fire contains energy. If you have more fire, you have more energy, all right? So all of this, the whole point, obviously these are probably very, commonsensical. It's very intuitive. It's like, well, yeah, of course I have more fire, I have more energy. But what I want you to start thinking about is the fact that energy is an amount of something. So there is energy in fire. If you have more fire, you have more energy. If you have more gasoline, you have more energy. If you have more wood, if you have more coal, if you have more of any type of matter, you have more energy. So it's an amount. You can sort of say, you could calculate how much more energy is in this house fire than is in this match, depending on the amount of fuel and all that kind of stuff. Okay, so you can really quantify energy, and we're going to go over how to quantify energy shortly here. All right, so hopefully that helps you kind of wrap your mind around what energy means. So all this relates to thermodynamics, okay? So thermodynamics, this was in your reading, and I believe in your video also. So if you think about what thermodynamics is, there's this sort of stuffy definition, the branch of physics which deals with the energy and work of a system. That's from NASA. A way to think of it is how the study of how energy moves in and between systems. So energy is constantly being moved around, it's being converted, like in that earlier example, you burned a match, energy is going from the inside of the wood, then it's being released through the fire, okay? Then the energy sort of dissipates. If you think about the gasoline, if you burn gasoline in your car engine, um, it starts out as energy, then it's converted into heat, and then it's converted into mechanical energy that spins, that pumps the pistons and spins the crankshaft and all that sort of stuff. So the study of how energy is converted from place to place, how it sort of moves around the system, that's just generally speaking called thermodynamics. Okay, and if you think about thermodynamics, thermo and dynamics. So if you don't remember, so thermo means, we usually think of it as heat, like a thermometer or thermos, whatever. So thermo means, energy or heat, and dynamics just means movement, right? So it's this thermodynamics is the study of how heat moves around in a system. Okay, so that's thermodynamics. Anytime you're studying energy and how it's moving, being used, being conserved, and so forth, that involves thermodynamics. So the first law of thermodynamics, also called the law of conservation of energy, is that energy cannot be created or destroyed. It can only change forms, right? This is one of those, mysteries of the universe. It's just the way things are. As far as we know, energy cannot be created, cannot be destroyed. This is often called the law of conservation of energy, probably for obvious reasons. Energy doesn't go away, it never goes away, it never disappears. So by extension, all the energy that's here in the universe now has always existed in the universe. Yeah, I know it kind of blows, a little bit mind-blowing, but that's, as far as we know, that's how it works, okay? We've never been able to prove that energy disappears. Now, it can change forms and does change forms constantly, but it cannot disappear. Really important, fundamental. So we have the two sort of basic categories of energy, the forms of energy. Um, And the two broad categories or types of energy are potential and kinetic. Okay, potential you can think of as stored energy. All right, kinetic is just you can think of as the energy of motion. Okay, so anything that's moving, even at a molecular level or an atomic level, does have kinetic energy. So even down to the electrons moving in the nucleus of an atom, that is kinetic energy because the electrons are moving. Potential energy is stored energy. It's energy that's not moving at the moment, but it's just sort of there. You can think of a coiled up spring. Anything that's made of matter, a piece of wood, that's chemical energy. Okay, there's chemical energy stored inside the wood. Gasoline, there's energy in the gasoline. It's just stored there until you release it by burning it or whatever. So there's a couple different types within the two major, there's some forms within the two major types. So potential, you can have nuclear potential energy, chemical potential energy, mechanical potential energy, and gravitational potential energy. Um, Nuclear, anything that has a nucleus has nuclear energy. So if you can split the nucleus apart into its components, it's going to release a bunch of energy. That's nuclear energy. It's there. It's not doing anything. It's just stored. It's what's holding the nucleus together. If you can split it, then it'll release its energy. Chemical energy is just energy that's stored in the bonds between atoms and molecules. So, wood is chemical energy, has a bunch of chemical energy by virtue of the components of the wood, mostly carbon, being held together in a solid form. Well, there's energy in those bonds. They're not doing anything, they're just sitting there, they're stored. But then when you burn the wood, you actually release the energy from those chemical bonds. Mechanical energy, you can have mechanical stored energy, think of a spring that you coil up. Gravitational potential, anything that's above, the ground, has gravitational potential energy. And then we have energy of motion. We have electrical, electromagnetic, or radiant. We have thermal, motion, and sonic. So sonic is just sound. So sound waves, they move through the air. Motion, sometimes called mechanical energy. Basically, if you have a physical object that's moving in some way, shape, or form, ball rolling down a hill, a car moving across the road, a fan blade spinning, whatever. Thermal energy is actually energy that's stored inside of materials, and it's vibration of molecules. We'll go over that in a later lesson. Electromagnetic or radiant energy, so sunlight's electromagnetic. It travels in a sort of a wave, um, and that's considered electromagnetic energy. It's moving. Radiant is the same thing. Um, and then the electrical energy is just the movement of electrons, okay? So again, the electrons are moving. They are motion. Any energy that's in motion is going to be kinetic. Energy that's stored is going to be potential, and there's all these different kinds. And I want to point out that these forms of energy are constantly being converted into each other, constantly. I mean, chemical energy is being converted to radiant energy when you burn stuff. You know, radiant energy and thermal energy and a car engine or a power plant is being converted into energy of motion. If it's a power plant, then that's being converted into electrical energy. If you listen to a motor run, you know that there's sound coming out of it. Well, any sound that comes out of a motor that's running comes from energy. It's energy of vibration that creates those sound waves. So sound is actually a form of energy that's converted from a different form. All right, so all of these forms of energy are constantly being converted back and forth all the time. Okay. So what I want you to do, you can go ahead and do this wherever you are. Take out a piece of paper, write down as many examples of energy in the room or wherever you're sitting as you can think of. Okay. So go ahead and do that, and I want you to list what is the object, is it potential or kinetic, and what form is this. So we'll go over this in class, but or I'll go over it in a separate presentation. Okay. So we'll go over this at a later time, but basically almost all the energy we use comes from the sun. We'll go over this later. Okay, this is another activity that we'll do in class, but you're welcome to do this at home. So we might also do this in a separate presentation, but I want you to trace the energy back from this manifestation of it. So, like the sound of my voice right now, that's sound waves, that's sonic energy, it's kinetic energy, sonic energy. So I want you to trace that back. So where did that energy come from? Remember, that energy had to come from somewhere else. Okay, so that sound energy that's coming out, that's being recorded right now, its energy, that energy was not created by me. That energy was converted by me. Okay, so I want you to think about that. When you talk and your voice carries out, that is energy moving through the air. Okay, so trace that back as far back as you can to its original source. So where did that energy come from directly? And then where did that energy come from? So trace all the steps back. Okay, so I also want you to think about driving to school or driving to work, whatever, driving a car. So there's energy, think about the energy that's turning the wheels. So where does that energy come from? So again, trace it backwards. You know, you think of it as the wheels turning, and then you kind of trace it back to the, the crankshaft or whatever. That gets traced back to the pistons. That gets, ultimately you're going back to the gasoline, and then you keep going back. So where did the gasoline get its energy from? So I want you to think of it like all of these are energy that came from a source. And then, a projector, or you could think of the screen that you're looking at right now. So trace that back. Where did that energy come from? What type of energy is it? Is it kinetic? Is it potential? Is it all of these different kinds? Okay, so go ahead and do that, and we'll go over those. I'll go over those in a different presentation, or we'll go over them in class. Okay, so the last thing we're going to do is go over units. Okay, so energy units are really, really important in this class. One of the main things you're going to be doing is dealing with units. So what is a unit? So I want you to press pause and think about just for a second, what do we mean when we say a unit? So a unit of something when we're talking about in science. So a unit is just a way to express a quantity of something, an amount of something, okay? So time, use them all the time. Time, what time is it? How long before this class is over, right? How much longer is this video? That's a unit, right? So you can quantify time in minutes, seconds, hours, days, whatever. Length, right? So how far is it to your house from where you are right now? You can express it in miles, you can express it in kilometers, you can express it in feet. Those are all different units. Velocity, like how fast are you going? Volume, how big is it? It's three-dimensional. Weight, etc. All of these are just units. So you use units all the time. You may not, you just may not be thinking of it. I mean, even when you talk about money, dollars are a unit of money. You can convert that to, British pounds or the euro or rupees or whatever. So units are just a way to express a quantity, and the thing is, you can express the exact same thing, the exact same amount of something, using different units, and it doesn't change the amount, it just changes the unit that you use. So the basic imperial or English unit of energy is the British thermal unit, or the BTU. Okay, so the BTU is the amount of energy it takes to heat up 1 pound of water 1 degree Fahrenheit. Let me repeat that because this is what defines a BTU. It's the amount of energy required to heat up 1 pound of pure water 1 degree Fahrenheit. If you want to visualize it, if you would light a wooden match and let it burn all the way down, that's about 1 BTU worth of heat. Okay, so that's our fundamental unit we're going to be using a lot in this class. It's used a lot in the energy field, more so than the metric unit, which is joules. So we're going to focus on BTUs for right now, and you'll be using BTUs a lot in your unit conversions and in various aspects of this class. Okay, so BTU is defined as the amount of energy it takes to heat up 1 pound of pure water 1 degree Fahrenheit. Okay, so here are some other energy units. We have a kilowatt hour, which is electricity, BTU. CCF, or 100 cubic feet of natural gas, that's natural gas, the most common unit you'll see there. Gallons of heating oil, that's an energy unit, gallons. A gallon of gasoline is different. Gallon of propane, and a joule. These are all energy units. And guess what? You can convert any of this unit to any other unit if you know the conversion factor. So what's a conversion factor? It's really just an equivalency, right? So we're going to go to BTUs. So we're going to take all of these different units, kilowatt hour, BTU, CCF, and so forth, and we're just going to convert it to the equivalent amount of BTUs, okay? So remember, a unit is just an amount of something. It's a way to express the quantity. And so you can take the same exact amount, the same quantity, and express it in different ways. Okay, so 1 kilowatt hour is equivalent to 3,412 BTUs. You're going to use this conversion a lot in this class. Really important to know. But 1 kilowatt hour is the same. It's the same exact thing as 3,412 BTUs. It's just a different way to say it. Okay. 1 BTU obviously is 1 BTU. A CCF, 100 cubic feet of natural gas, is about 103,000 BTUs or 102,500 BTUs, depending on the purity of the natural gas. Okay. So again, a kilowatt hour is worth, a little over 3,000, 3,500. CCF about 103,000. Fuel oil is about 138,000, a gallon of fuel oil, whereas a gallon of gasoline is about 125,000 BTU. So you can say you can have a gallon of each. This is basically fuel oil is diesel fuel, and gasoline is the stuff you put in your car. Well, the regular non-diesel stuff that you put in your car. So you can see it's a gallon. You would think, well, it's a gallon of one thing, it's a gallon of another. It smells like gas. It's probably the same thing. Actually, as it turns out, fuel oil is more energy dense. It has more energy, more BTUs of energy than the same amount of gasoline. Propane, which is also can be liquid, is only 98,000 BTUs per gallon. All right, so you can see each of these are a gallon, but it's important to know what type of gallon or gallon of what type of substance you are using. Okay, it makes a really big difference. And then a joule is actually a tiny fraction of a BTU. So the key here is that all of these energy units can be converted. Again, you can convert any unit to any other unit if you know the conversion factor. This is really important. So if I know BTUs, I can convert to kilowatt hours. It doesn't matter how many I have, I can convert. If I know BTUs, I can convert to CCFs, equivalent CCFs. I can convert to equivalent gallons of fuel oil. It doesn't matter. I can go back and forth. I could take a couple steps and convert fuel oil to CCFs. I could go from fuel oil to BTUs and BTUs to CCFs, right? So it doesn't matter. If I know my conversion factor, and these are all conversion factors, if I know my conversion factor, I can convert any unit into any other unit. This is absolutely essential to understand for this class, absolutely essential to understand for energy managers, anyone working in the energy field, that energy is just an amount of something. Units are different ways to express that amount, and if you know the conversion factor between two units, you can convert to back and forth between those units. Okay, so we're going to go over some examples of this in the next demonstration and lecture.